Good afternoon, everyone. The Atom Student Group is pleased to have with us once again Professor Richard Elliott. He is currently a Professor Emeritus at the Chemical, Biomolecular, and Corrosion Engineering program at the University of Akron, USA. Professor Elliott is co-author of well-known books, Introductory Chemical Engineering, Thermodynamics, and the Property of Gases and Liquids, a reference book to chemical process design engineers. Among his research interests, we can highlight thermodynamics of hydrogen bonding, molecular simulation, perturbation theory and integral equation theory, experimental phase equilibrium measurement, chemical reaction engineering, supercritical fluid processing, and microcellular forms. Professor Elliott has published over 100 articles in international journals, which to date have been cited more than 2,000 times. So welcome back, Professor Elliott. We are very pleased to have you here, and you now have the stage, albeit virtual, given the current circumstances.
So I've got only about 27 slides, but they're a little bit dense, and but I don't want to go too far over time. So I did badly on that in the previous presentation. So I might go over some things that maybe you're a little too confusing and you want to go back and talk about those. Just write them into the chat while you're thinking of it, or take notes, and then don't hesitate to ask any questions that I might confuse you about. So previously we talked about the artifact-free equations of state, and then force field development using surrogate models like M-bar, but also equations of state can serve as tools for leveraging our simulation results and getting us to a practical engineering model from the rigorous statistical mechanics in a shorter time frame. So that's, I'll just briefly mention a couple of those highlights there. We talked about Zwanzig's analysis, and we took it up to the second order perturbation theory. Very straightforward extension of the same principles. You get the third order and the fourth order theory. And I'd like to show you what happens when you implement that theory. It's pretty interesting. Just by adding higher order TPT terms. The problem is that, and this is why it wasn't done long ago, it's hard to get good statistics. So you need a really long simulation in order to get meaningful results for these third order and fourth order terms. And even then, the uncertainty in those numbers is much higher than we're accustomed to with the first and second order. The interesting part is, if you take the ratio of those terms, you start to see some trends that will help you interpret the results and get meaningful results, even though the uncertainty may be a little bit higher than you would be comfortable with normally. And one of those tools that you can use to leverage your insights is that in the low density limit, this ratio actually has a known value. It's the second virial coefficient to third order in order to represent A3 at low density, and the second virial coefficient at second order represents the A2 at low density. And those numbers are relatively easy to calculate. And in fact, I'm going to show you how easy. And hopefully, one of the things I want to convince you of is that you can do this. You can calculate your second virial coefficients, and it's a worthwhile thing to do. It's easy too, and fast. and so then, if we just knew something about the third virial coefficient, we would be able to characterize these third order, fourth order terms completely. And that works for the square wall spheres. At this moment, it doesn't work as well for Lennard-Jones spheres or Lennard-Jones chains. Well, that's just looking so far at B2 and B3. It turns out we can also learn things from looking at the fourth virial coefficient, the fifth virial coefficient, and the sixth virial coefficient. And so I'll talk a little bit about that. That generates something called, what I call a perturbative virial series. So in other words, you get a series in density for the A naught term. Turns out you've been using that for years and years. You just probably didn't call it that. But that's a series in density that has virial coefficients. And I'll tell you right now what it is. It's the virial series for the hard spheres. You re-sum that, you renormalize it, and you call it the Carnahan-Starling equation. Okay, so this A naught term in the resummed perturbative virial series, you've been using that all your life probably. So that's actually something quite familiar. Well, why can't we do that for the A1 term instead of just the A naught term? Turns out we can. Well, why stop at A1? How about A2, A3, A4? So it turns out it works pretty well. And it works even better. So it's a little counterintuitive. It works better for the Lennard-Jones chains and Lennard-Jones spheres than it does for the square-well sphere. And I'll try to explain why that is. And it has a lot to do with what we've been talking about before in terms of this square shoulder and why that causes problems. And the shapes of these first order and second order perturbation contributions, and of course then the third order and fourth order. So this is just a brief review then, and you'll remember that we talked about what we mean by the equation of state in terms of the Helmholtz energy, the residual Helmholtz energy, and how the A1 term is really just a kind of a mean, and the second order term is kind of a variance. And another thing we talked a lot about, and this is the talk where I'm hoping to finally bring this point home, is that when we renormalize or resum our series, we can get good accuracy from a relatively small number of coefficients. And the key to that is recognizing something about the physics that's driving the behavior behind that series. So here's the Carnahan-Starling equation, for instance. And these are the virial coefficients that you get from the Carnahan-Starling equation. If you go back and you read the Carnahan-Starling equation paper, you'll see that this is exactly how they inferred the functional form that they got. They looked at the first few virial coefficients. The 4 and 10 are exact. The 18 is supposed to be 18.365. And they looked at that and they said, 1, 2, skip a few, 100. And said, that's close enough. And so they reorganized resummed their series, and they got this functional form. And that's driven by, the physical thing that's driving that series is the divergence at closest packing. Well, actually at 1 minus eta, that's at complete filling of all space, which we know you can't do with anything that doesn't tessellate, okay? So spheres, certainly, you can't even get to complete filling. But it turns out that does a really good job of describing the hard sphere equation of state. In the ESD equation, we wanted something simpler. As you recall, we wanted a cubic equation so we could eliminate all artifacts. Well, that means we have to make another assumption about what's driving that divergence and driving the series. And you never get anything for free. So you have a simpler functional form here, and you don't get as good a match with the known values of the virial coefficients. A different kind of renormalization in a lot of, when you talk about the virial series, you're talking about series and density. But this is a renormalization with respect to temperature, or beta, 1 over temperature. And so what you see is that by having y, which is 1 minus, well, exponential of beta minus 1, okay, you expand the exponential, and you see that you get this functional form. Okay, so now we can have renormalizations with respect to temperature as well as density. Another renormalization that you may be familiar with is what occurs in chemical theory. In order to get the total number of monomers divided by the true number of molecules in the mixture, well, you have to multiply the fraction of monomers times 2 to get the number of dimers. And you do 3 for trimers. Well, how many trimers do you have? Well, you have the mole fraction times Ka squared, okay? Then for the number of tetramers, it's going to be cubed, and you get this infinite series that's basically 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the 4th, on and on and on. And if you look up that summation in a standard math handbook, you'll see that that's the summation for 1 over 1 minus x squared. And you rearrange that, and you get the result of Wertheim's theory. Okay, because this infinite equilibrium model and Wertheim's theory for the polymerization are exactly the same. So these renormalizations occur everywhere, and you just maybe you did, maybe didn't fully recognize exactly what's going on there and appreciate the power of that renormalization concept. So then let's review then about deriving these perturbation contributions. We just take the Helmholtz energy, expand the partition function. What is the definition of the configuration integral? We separate the, we recognize that we multiply and divide by this exponential of the reference part. And then we recognize that the exponential of the sum is the product of the exponentials. And when we pull that out, we see that we've got this exponential of the repulsive part multiplying some weighted part here. Well, this part here, the first integral, that just becomes the partition or configuration integral for the reference system, okay? So that's just shorthand there. And here I've just expanded the exponential, and we see that we have this very common form where we've got a weighting factor times a quantity that we're summing divided by the sum of all the weighting factors. And that's just the standard definition of an average, a weighted average. And in this case, we call that an ensemble average. So then we can rearrange that and recognize that the exponential of the attractive part is really just the ensemble average of the exponentials of these beta u's. Then we can expand both sides and match these weighting factors, okay, W1 and W2. And when we do that, we see that A1 is this group, A2 is the n squared minus n squared. And if we were just to add one more term here, okay, W3 beta cubed over 3 factorial, okay, this one is going to be the same thing, cubed over 3 factorial. And then we see that A3 is given by this relatively simple formula. This was described by Del Rio and co-workers in 2009. He's done a lot of work over the years with the square well fluid. And also A4. And Del Rio actually calculated these quantities in 2009. And Pavlukin did it again in 2012. And Zhu and Solana did it again in 2013. And all of their results agree pretty well. One of the reasons why the square well was done first is we only have the one well, so we really only have to calculate these numbers inside the wells, these averages, for the one well, not over a series of distances like you'd have to do for a Lennard-Jones fluid. So it's an easier thing to calculate. Another beautiful thing here is that the reference system is just the hard sphere system. And so the algorithms for simulating that and doing it for a very, very long time so that you can add up your statistics and get your uncertainties down, the algorithms for that are very well developed and very highly efficient. So that's how we were able to get these perturbation contributions. Well, what happens then when you incorporate those new perturbation contributions? Well, here we're comparing the equation of state to the simulation results, and here's the deficiency that you see. You see that with first order perturbation theory, you're missing the critical point by a long, long way. Second order perturbation theory, well, you're getting better, but you're still pretty far from where you'd like to be. Third order actually gives you a pretty big jump. Fourth order, it's a little better than third order, but we're not increasing as quickly as we'd like to. So each additional order is kind of slowly creeping up on the answer. How can we get to this infinite order? That's the trick that I like to show you. And the trick that I'm going to show you is not renormalization group theory. So it has a limitation. With second order perturbation theory, your critical exponent, which is basically when you plot the log of the liquid density minus the vapor density versus the log of 1 minus the reduced temperature. Okay, imagine, what that looks like. It says 1 minus reduced temperature, or says that the difference between these etas looks as 1 minus temperature to an exponent. And that exponent is known from multiple different theories to be 0.325. But the van der Waals equation of state and PC-Saft equation of state and all the classical equations of state give you about 0.5 up to, well, after you reach 0.9. So remember, 1 minus TR, and the negative of the log of that, when you get to 1, that means you're at 0.9. When you get to 2, you're at 0.99. All right? And so your traditional PC-Saft second order perturbation theory is going to get 0.325 up to about here, and then it's going to launch off at 0.5 slope. But with second order, with this Gaussian extrapolation that I want to show you, we can go all the way up to a little bit better, actually, than 0.99. And then we see the slope change to the classical 0.5. So the result is not entirely non-classical, but it gets you 10 times closer to the answer than what you get with second order perturbation theory. When we look at the behavior of the internal energy, we see that as we go up in order, it's getting better and better, but we're still not capturing this divergence. So there's a divergence in the heat capacity that is at about, the exponent on that is about 0.11. So whereas this is 0.3, 0.11 is a very weak divergence. But you can see it when you plot your internal energy versus reciprocal temperature for the square well fluid. So what is this infinite order renormalization that I'm talking about here? We can also talk about Lennard-Jones spheres, and we see a similar trend. The good news is with fifth order TPT, we're getting close to a reasonable result. There's a little bit of weirdness going on in the shape of this curve. And it's an indication that when it comes to calculating these third and fourth order perturbation contributions for Lennard-Jones spheres, because it's a continuous potential, it's much harder to get the uncertainty down. And so these data were actually the fourth order contribution for Lennard-Jones spheres was first calculated by Joachim Gross and his coworker Ties van Westen in 2017. So this is a relatively new result, and they were only able to get viable results up to about 0.08 packing fraction. So relatively low packing fraction. Beyond that, their uncertainties were so high that they just gave up. And the result is, even for vapor pressure, we get pretty good results, agreement with the NIST standard values. The biggest impact is on the flattening this binodal curve in the critical region. The only thing that's happening along this PSAT curve is that you will be able to calculate a PSAT with first order perturbation theory up to the critical temperature, which is about 1.4 in first order. And so it's supposed to be about 1.25, 1.26. Oh no, maybe, it's 1.32. Sorry, I forgot. Yeah, it's different for the square well spheres. Yeah, so I think the given answer is 1.32 in the latest results. We could use the same procedure that we used for square well spheres to generate an infinite order result, but there's some things going on that give me pause for doing that. Nevertheless, just the fourth and fifth order get a pretty flat binodal. But remember, the fourth order was only calculated to a packing fraction, or on this scale, rho, of 0.16, okay? So about right there was about the highest density that their calculations go. So about half, not even halfway to the critical density. So that makes it hard to figure out what's happening in the critical region and over to the liquid region. So we need some methodology to even extrapolate the fourth order results. And the fifth order is a complete extrapolation. We don't have any simulation data there at all. So how can we do those extrapolations? Well, we're going to have to analyze the trends that we see in these TPT contributions, the thermodynamic perturbation theory contributions. Well, we've talked about Lennard-Jones, the square well spheres many times, and you recognize this A2 termed contribution. I took the negative of it here so that we could just put it on a positive axis. And you see this old square shoulder here that's always so annoying. The first order contribution, I had to divide it by 10 just to get it on scale here. So you could see all of them at the same time. The A3 contribution has this functionality where it goes up near the critical density, reaches a peak, and comes back down. So that's what we saw also for the A2 contribution of Lennard-Jones spheres and for the speed MD chains and all of those other kinds of molecules. They didn't have that square shoulder, right? So they just had a maximum in A2 near the critical density, and then they decayed to zero. So it's interesting. The A3 term looks a lot like that, and the square shoulder has gone away even for the square well spheres. And the A4 term, again, has this peak near the critical density, and then it decays to zero. What about the A3 term for the Lennard-Jones spheres? We see that it has a peak, has that same qualitative behavior. And here are the three curves that Van Westen and Gross were able to compute for the fourth order contribution. Since the fourth order spheres, square well spheres do that, maybe we can assume that the Lennard-Jones spheres would probably do the same thing. So these curves all look the same. And if we had the capability running today for me to ask the audience a question, I would put this question out, and it'd be interesting to see what the answers would be, okay? But I think it's just going to take too much time to do that. So I'm just going to sort of put this question out there and let you think about it for a second. Which one of these peaks is sharper? Or are they basically the same sharpness? So at first, it looks to me like the second order term is a sharper peak, right? It goes further down and then it comes back to zero. So it looks like it goes further down and then, you know, the depth to this height at 0.8, maybe that's a sharper peak. On the other hand, this one's a lot closer to zero, and 0 divided by anything is still 0. So maybe that's the sharper peak. Or maybe they're both equally sharp. What can we do to figure out whether it's sharper or not? Okay? Let's just take the ratio, divide this by that, and plot it as a function of density. If it's perfectly flat, that means that they're equally sharp, okay? And all we need is a scale factor to multiply the A2, and we'll get the A3. And if we can figure out that scale factor again, we can get the A4. Wouldn't that be great? We can maybe get to infinity that way. On the other hand, if one is sharper than the other, maybe we can use that information too. So let's look at the ratios and see what they look like. So what we get when we plot A3 over A2 is this result, okay? And when we plot A4 over A3, we get this result. Interestingly, we can do the same thing for the Lennard-Jones spheres. And we see a kind of peak like that. This is the same peak for methane. When we look at butane and even dodecane, we see this same kind of behavior. You can see that the uncertainty is getting larger as we go to longer chains. It's harder to do the simulations for the longer chains. They're just, everything takes longer for longer chains. So the statistics are getting worse. And remember, when we divide two numbers, we're dealing with the uncertainty of each number. And out at high densities, we're dividing 0 by 0. So the uncertainty is just going nuts. It's amazing that we can get any results at all, you know, at these high densities where we're dividing 0 by 0. Interestingly, for the spheres and the chains, the maximum is occurring pretty close to the critical density. This is pretty close to the critical density of about 0.15 for square well spheres. The only one that's falling out of line is the A3 over A2 for the square well spheres. And why is that? Again, it's the square shoulder, okay? Because if you divide this number by this artificially high large number here, you get a smaller number, and that shifts the ratio to the left. So I consider that to be an annoyance. It's not a real effect. It's an artifact of that square shoulder that's sort of driving things in the wrong direction. What the data are really trying to tell us here is that the peak for this third order term ought to be at the critical density, and when we go to make our estimates, we'll just have to make an adjustment for the square shoulder effect. So what kind of function has that shape? And I think if I artificially extend the density scale, you'll see too that this is a bell-shaped curve. That's a Gaussian curve. So to interpolate these results, and I can say that this interpolation is a quantitative interpolation because the error in the curve in the interpolation is smaller than the uncertainty in the data. Now, it's a cheating way of saying that, right? Because the uncertainty in the data is so horrible. But it's a quantitative correlation. The curve is at least as accurate as the data. All right? And so this is a great interpolation function for these data. Another thing that you might know or might be aware of is that when you look at these multi-parameter equations of state, like NIST uses for fitting data, and they have like 52 parameters in them, they also include these kind of Gaussian terms that they've just evolved to over, decades. They just found, hey, if we throw a term in there like that, it fits the data better. Well, now we have a good explanation for why those terms need to be in there. They're taking care of our third order term, our fourth order term, and the fact that the third order term is so peaked at the critical point is an indication that we can think of our third order term as the fluctuations in the second order term, which is a fluctuation term. So our third order term is the fluctuations in the fluctuations, and the fourth order term is the fluctuations in the fluctuations of the fluctuations. And we see that all of those things are getting more and more peaked and sharper fluctuations more and more at the critical point. And it's just kind of amazing the extent to which these fluctuations are just maxing out right there at that critical density. And it's all reflected in your perturbation contributions. We can develop a correlation then for A4 over A3. And you can see we're starting to get some really big scatter out here when we divide 0 by 0. And this is on a log scale. Okay, so those are big variables, big uncertainties out here. But remember, when we take it off the log scale, these numbers, most of them are all 0 anyway. And so what we can do is estimate our A4 from our A3. And so even though the uncertainty is really bad in A4, we can get reasonable trends for that. Another thing is the ratio at low density of these things, and I hinted about this before, is just equal to the second virial coefficient at that order divided by the second coefficient at the next lowest order. And for the square well spheres, that's a beautiful thing because we know the second virial coefficient and the third virial coefficient actually analytically for the square well spheres. So it's no problem to get 100% accuracy for our second virial coefficients. So we know what this intercept is exactly. And the interesting thing is, it's the same number. For all of these different well widths, the intercept is the exact same. If you were just looking at the simulation results, you would say, oh, that's not right. The simulation results are showing a different intercept for this really wide well and a narrow intercept for the really narrow well. And this analysis shows you the exact result. The exact result is exactly 0.25. It's nice to have exact results when you can get them. And then this leads to this kind of binodal behavior that we've talked about before. Well, a nice thing about the analytical solution for the second virial coefficient for square wells is we know this intercept to infinite order. So what if we were to apply a similar procedure and say, well, we know what the density is where these quantities are reaching their maximum. So we know the density where the Gaussian is. We know that's the critical density. We know the intercept. The only thing we don't know is what is this dispersion term for the Gaussian at each order. If we rearrange the square well spheres, we can see that we can determine that from the third virial coefficient. And in a perfect world, the exact third virial coefficient for the exact same lambda would fit the data perfectly. When we tried to develop this graph, that didn't work out quite as well as we would have liked. And so we had to come up with an effective value of lambda that's like 1.1 times the actual value of lambda. And that's the one that makes it fit, so that we're able to calculate the fourth order contribution from the third order contribution. For any value of lambda, we just have to tweak the lambda a little bit. And then we've got the entire equation of state. If we make another assumption that this G1 contribution always follows that tweaked result, even for, or basically we want to assume that G1 for the fifth order divided by fourth order is the same as the G1 for the fourth divided by the third. So we're going to take that G1 and make it into a constant. If we make that a constant, then we get this recursion relationship that we can calculate the next highest order term from the next lowest order contribution. And then we can write this as the A2 term times this exponential of 1 minus, of exponential minus 1 minus the first order term minus the second order term. Why? Well, when we add all this up, it ought to be 1 plus the third order term plus the fourth order term, because we've already got the A1, the A2, and the A0 accounted for. So the thing that comes after this one ought to be the third order term. And that's what we'll get when we subtract off the first order and second order terms of this exponential. The next term in the series will be the third order contribution. And so what we've got then is an infinite series in closed form. In other words, a renormalization. And I'm not saying that this is the perfect renormalization for every potential model in the world, but for square well spheres, we tried it and it works pretty well. And so when I write infinity over here, this is what I'm talking about. A renormalization with respect to temperature. We can do the same thing for Lennard-Jones spheres. And this is what the ratio looks like. The bad news is, according to the simulation results that we have so far, even though we can describe how this intercept is changing, because we can develop a really accurate perturbation expansion for the Lennard-Jones fluid. So remember, we had an analytical solution for the square well spheres. So we're on our own to develop it for Lennard-Jones spheres. That's not to say that there isn't an analytical solution for the second virial coefficient of Lennard-Jones spheres. There is, but it's an expansion that's not in beta. It's beta to some weird powers, okay, exponents, and we need it to be for this Zwanzig's perturbation theory. We need our betas to be to integer powers, and so we have to reorganize the analytical solution to get this perturbation series expansion that's pretty accurate. Okay, I'm not saying it's I think the RMS error was about 0.03 over the entire range of temperature, and these numbers are running from 50 to negative 1,000. So the trick to this is to get the second virial coefficient of the reference contribution accurate, and once you've got that, that underlies the contributions for all the higher order second virial coefficient contributions. We're going to assume that it's symmetric, and so we have this G function that gives us our recursion relationship. In this case, for the Lennard-Jones spheres, the third virial coefficient estimate of what G1 is, that didn't work out so well. I couldn't figure out how to make that work. And so I just fit that G1 value to the Van Westen and Gross. So the thing that's happening here that's bothering me is that the intercept is pretty much following what we know it has to be. Well, that's good, okay? But the peak, the magnitude of this peak is much, much larger at each increasing order. What bothers me about that is that if the magnitude of your fourth order term is larger than the magnitude of your third order term, is that series converging? And it looks like maybe the fifth order term is even worse. So are we really operating in a region where this series with respect to temperature is converging? It's not so much the series with respect to density that's bothering me. So at this moment, the best I can do is say I've made my best estimates for what the third order, fourth order, and fifth order TPT contributions must be by kind of extrapolating what the trends that we see. And that's the basis then for computing this equation of state. I'll show you one more thing that I sort of alluded to, but we didn't see it quite so clearly. So in previous calculations, we've shown ratios of these AIs. Here I'm plotting the AI by itself. And what you can see is that it's getting steadily sharper and sharper and sharper and narrower around that critical density. And that's all an implication of the Gaussian extrapolation that we're doing. There's an alternative way of doing this that Fred has alluded to, and it's called the renormalization group method. And actually, the 1982 Nobel Prize was awarded to Kenneth Wilson for developing this renormalization group method, which he applied to some critical phenomena, quantum phenomena. But it was quickly shown that it could be adapted to describing critical points of vapor-liquid equilibria. So for many years, people have been adapting that renormalization group method, and the most widely recognized method, I think, is this White's method. And again, it's a recursion relationship that you develop. And in this case, the way it works is you have to lay down a grid along the isotherm that you're calculating, and then perform that recursion out to a very high density where you feel confident that the fluctuations are zero, and therefore you just kind of truncate your series and say, okay, the series contribution is negligible now. I'm just going to ignore that and then assume that it's equal to the perturbation theory result without the renormalization group added. And then you have to do the same thing again, another recursion out to zero density, to where you just accept the perturbation theory result at the low density end. And you're kind of like, it's a crossover is one way of describing it, from the perturbation theory outside the critical region to the renormalization group theory inside the critical region. It's very difficult to do that in a way that keeps all of your derivatives continuous. It's also very slow, because for every single state point, you have to develop this recursion grid out to all this high density and low density calculations at every single density and temperature. You have to do the recursion out to high density and low density. And that recursion procedure takes time. And then if you want to calculate another Z factor at a different density, because you're going to guess and guess again to get your Z factors right, the way that we always do, well, you got to do another recursion relationship and do that whole renormalization again. So it's extremely painfully slow. You can read more about that, not just from this paper, but this paper will give you a lot more papers to read where they've applied the method, and we describe, our perspective on it And one of the things we found is that the van der Waals loop, when you apply this method, is not a simple loop. It pretty much basically goes to the when you've done the recursion out to infinite number of recursions, your van der Waals loop goes to the saturation condition. It's flat all the way till the liquid density, and then it goes up again. So you don't really have a van der Waals loop. And so how do you interface that with density functional theory? It becomes awkward, let's say. Another thing is the renormalization group method. Well, it was developed for spheres, right? And so White never really thought about what would happen for chains. And some strange things happen when you try to adapt that method for very long chains. You get flat, 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 and then you can see that the cutoff here, this crossover here, is very strange. And the way that your derivative behavior is going to appear there, I would worry about that, okay? Whereas the Gaussian extrapolation gets you pretty much the same flatness of the binodal, but it avoids the artificiality of that cusp. When you go to calculate the state point from the Gaussian extrapolation, hey, you just plug it in a density and a temperature and you calculate the number. There's no recursion, there's no grid, super fast. So we've learned a lot from looking at this second virial coefficient and third virial coefficient, and maybe we can learn some more. What happens if we go ahead and incorporate fourth virial coefficients, fifth virial coefficients? We can define that in the way that Wertheim did when he developed his theory of associating fluids. The difference is Wertheim was able to group some of these diagrams and only keep the ones that had a single bond, okay? So this diagram would be accepted. This diagram has two attractive bonds to one site. Well, if you think about hydrogen bonding, once one bond is formed, a third molecule coming in would not be able to fit inside the two molecules in order to make two bonds to one site. That's called steric hindrance. And I think Professor Chapman talked about that during his lecture, right? So this diagram would be excluded. This diagram would be included. This diagram would be excluded, excluded, included. So by looking at all the diagrams that would be included, Wertheim was able to get a renormalization for the polymerization of those hydrogen bonds and the formation of hydrogen bonding chains that looks very much like that renormalization I showed on the second or third slide.
Richard,
Yes.
Can I suggest you to define the diagram? I think people are not familiar with this.
Okay, so here is a picture of the diagram right down here. Here's some examples, okay? And so what does this diagram mean? It means that we're going to take the integral of, when we're looking at a repulsive bond, it's one of these solid sticks, okay? And so we've got three of those solid sticks going all the way around. And when we've got a single bond like this, it means that we've got an attractive contribution between either 1 and 2 or 2 and 3 or 3 and 1, okay? And so this diagram would be the same if the bond was on this angle or this angle. You just rotated it around, right? So that's called a symmetry argument. And so the coefficient that you multiply this integral by depends on the symmetry of the diagram. And those symmetry numbers for each diagram are worked out and tabulated, and people know how to add those coefficients times the values of the integral. So what we're doing here is we're going to move these, let's set molecule 1 at the origin, and then we'll move molecule 2, and we'll calculate the repulsive energy between 1 and 2, 2 and 3, and 3 and 1, okay? And then we'll move molecule 2 again and calculate all of those things. Then, after we've done moving molecule 1, molecule 2, we'll put it back at some standard position and move molecule 3 and do this integral and add up all of those contributions. And I'll show you some very specific details of how that algorithm works for the second virial coefficient towards the end. I think it's like the 20th slide or something like that. And so here's another one to see if maybe you're catching on, because this one doesn't have as much symmetry as that one. I've got to specify, well, where are the attractive energies this time? So which two sites are going to have the attractive energy that I'm going to multiply by? So here I'm multiplying by the exponential of the repulsive energy. Here I'm multiplying by just the beta U of the attractive energy. But these are all things that you calculate straightforwardly from the definition of the Lennard-Jones potential and which part is attractive and which part is repulsive, which we talked about on slide 2 or so. And so these are just integrals that you've got to perform. And you could say, wow, there's a lot of integrals here. If you talk about traditional virial coefficients, there's only one of these triangular diagrams. You just compute the Meyer function of the full potential for one triangle, and you're done. We've got 6 for the TPT perturbative virial series, and we've only gone to third order. If we were going to go to fourth order, we would have a bunch more of these diagrams just for the third virial coefficient. Here I've done out to third order for the fourth virial coefficient. There are 38 diagrams here. Well, if we were doing this with the normal virial series, there would only be these 3 diagrams here, okay? The square, the diagonal, and the x, okay? So we've taken 3 diagrams and we've made them into 38. Are we going in the right direction? You could ask that, okay? It sounds like we're making a relatively simple problem much harder. But the good news, at least for square well spheres, is that once we calculate each of these contributions and collect the orders of the temperature, they don't have to be recalculated. If you change the temperature, you don't have to recalculate the diagram. You know what that coefficient is. You run the equation of state. And so we get a complete equation of state directly from this calculation of virial coefficients. Now, the number of diagrams may seem to be getting intimidating here, but Andrew Schultz has been working on this problem for many years. And one of the things that people do is they try to get higher and higher virial coefficients for the hard sphere fluid. For a couple of reasons, the higher we go with the number of coefficients, the closer we can get to figuring out what is that divergence that's driving the hard spheres. Is it really 1 minus eta cubed, or is it some other random close packing limit that's driving it to infinity? So people are very curious about that, and the way to figure it out is to go to higher and higher virial coefficients. Well, the number of virial coefficients grows exponentially as you go to higher and higher order. And so there's about 10,000 diagrams involved when it comes to the 12th virial coefficient just for hard spheres. So when I approached Andrew about, hey, you know, there's going to be a lot more diagrams when we do it this perturbation way, he said, how many? I said, it looks like 38 for 4. He laughed, you know, that was like a joke for him. That's easy, okay? So it's easy for Andrew. The good news is that the University of Buffalo is about a 3-hour drive from the University of Akron. So when we first started this work, I literally threw a computer in the backseat of the car, drove up to Buffalo and said, hey, Andrew, put all the programs I need on this computer, make sure they work, and then I'll drive home. And that's how we got this this work off the ground. Okay, so it looks like really we might be going in the wrong direction, but for Andrew Schultz, this is a trivial problem. And so we load up the code that he has, and we run the code. And there are things that we can learn. Because of the nature of square wall spheres, and it was Andrew who figured this out, not me, we get a finite series that is complete for each one of these virial coefficients, okay? It turns out we need 15 coefficients in order to, 16, I guess, if you count 0. So 16 coefficients to get the 6th virial coefficient, 11 for the 5th virial coefficient, 7 for the 4th virial coefficient, and you can see how it goes. The 3rd virial coefficient here, this is the analytical solution that Kihara derived in maybe earlier than 1958, actually. I think the book that I had was in 1958, but his derivation was actually earlier than that, but it was published in Japanese. And so it's nice that we have a complete series, a closed form series for each one of these. So we have finite series. If we were to expand these in beta epsilon, like our Zwanzig perturbation, okay, we would need an infinite series. And we can learn some things by looking at these curves. Maybe you've thought about the 3rd virial coefficient that you calculate from the PC-Saft equation. And what you'll see is it kind of comes down and goes up like this -2 line. Okay, the -2 corresponds to 2nd order in beta epsilon. So we're calculating what these coefficients would be by expanding the exponentials and collecting all the coefficients of beta epsilon squared, beta epsilon cubed. Okay, so that's what I mean by 2nd order here. Okay, and what we see is the 2nd order theory is going to be pretty good out to about a beta epsilon of about maybe 0.9. But the 3rd order theory, which we would think would be more accurate than the 2nd order theory, is actually worse because it's way up here. So what does that mean? How can the 3rd order estimate be worse than the 2nd order? Well, it's just a coincidence that the 2nd order is accurate. It's because the infinite order result turns around and goes down like this, right? If we kept going, 4th order would come out further. And the thing that you can't see is that this curve keeps going up and up and up, and then it comes down over here somewhere. So qualitatively, it's already showing the right behavior. It's just that we need more and more contributions in beta epsilon in order to actually recover this infinite order result. And so one of the points I'm trying to make here is that even though the PC-Saft equation is incapable of getting this 3rd virial coefficient right, it's exactly what it should be for a 2nd order theory. A 2nd order theory should only be able to behave like this. And so you've got to think about these coefficients and your orders with respect to temperature and your orders with respect to this exponential of beta epsilon in the right context. And that's one of the things that we learn from looking at the square wall spheres and calculating these virial coefficients, out to the 6th virial coefficient. Another thing, so now that we've got the coefficients at each order in temperature, let's add them up for the A1 term and see if we can get a closed form solution. And so what you see is when we have just the 2nd order term, so we got the 2nd virial coefficient, we just get a straight line. We're plotting versus density now. When we add the 3rd perturbative virial coefficient, we get a little closer. The 4th perturbative virial coefficient looks like it's going in the wrong direction. All right, we've seen that before. 5th virial gets a little closer. 6th virial goes away. Guess what? The 7th virial is going to get a little closer. And we see this going on back and forth behavior. But we couldn't find any kind of resummation that would absolutely nail this curve for both, for all the different lambdas that we were looking at. But we do know that there is this analytical solution for the Perkusiewicz, and we know that any analytical function of density can be expanded as a perturbation series, as a Taylor series. And so we know the series exists that at least describes the Perkusiewicz, and the Perkusiewicz is doing a very good job here of describing the A1 term. So we think we have a pretty convincing argument that this series expansion of A1 is converging. And that's enough, actually. If you think back about the binodal curve and the A1, we were calculating reasonable estimates of the liquid density and the vapor pressure with just the first order perturbation theory. So with the A naught, which is just the Carnahan-Starling, because the reference fluid for square wells is hard spheres, okay? Just A naught and A1, we're getting an equation of state from virial coefficients that's describing liquids. So that's a kind of an academic victory, you might call it, but we are using the virial series to calculate liquid properties and getting reasonable results. When it comes to the second order, with using a Pate approximate, we're eventually able to do a reasonable job out until we get into that square shoulder region, and then things just get ugly. Again, this square shoulder is still just being an annoyance. And why I call it an annoyance and not something really important is you can do an interesting experiment. So if you divide your potential function and use a square well out to 2 lambda, okay? Now, divide that 2.0 and say the second step is going to be either, is going to be a variable. And when that second step, when the depth of that second step is 0, I actually have the 1.5 fluid, right? So it's essentially equal to if the lambda was just going out to 1.5, if the depth of the second well is 0. When the depth of the second well is equal to the depth of the first well, well then you've got the 2.0 lambda. What happens when you vary the depth of that second step? Well, you would think you would just smoothly go from the 1.5 fluid to the 2.0 fluid, but that's not what happens. You actually go in this direction until you get to like 95%, of course, of the second well. The first thing that happens is the fluctuation due to the square shoulder gets smaller, and that makes perfect sense because you're getting your step potential is now looking more like the Lennard-Jones fluid, where those things don't exist. And so that's why I say that this square well fluid, this square shoulder, is really just an annoyance. It's an artifact of the square well potential function. As we go to higher and higher order, we couldn't even find a Pate approximate that worked very well. Okay, so that's where, well, we would just use the Gaussian extrapolation then to infer what's happening at these higher order coefficients. What happens when we look at Lennard-Jones spheres? Well, an amazing thing that happens first is we figure out that all we have to do is multiply by an effective diameter of the hard sphere and multiply that by the corresponding virial coefficient for hard spheres, and we get an amazingly good approximation. And when I saw this, I said, wow, that's so simple. It reminds me of this quote from Albert Einstein, okay? And so this is the correlation that we developed. It's in that 2019 paper for Lennard-Jones spheres, and it's actually a slight modification of a correlation I developed way back in 1986. When it comes to looking at the higher order perturbation contributions, those are very smooth. You can see the B2 naught sort of in the background behind each one of these individual contributions. And so we have to sum that up. And so you see that that's happening at every order in temperature. That's why this Y function is multiplying B2 naught. And that's how this infinite order estimate then develops for the second virial coefficient. Well, we can do a similar thing for the so here we're looking at the higher order virial coefficients. Okay, so that's going to give us the complete equation of state for the reference fluid, the Weeks-Chandler-Anderson reference fluid. What we find is that we need to use another renormalization pretty similar to what Carnahan developed. And then instead of just using a straightforward power series, so we still need a little bit of a renormalization there in order to make the dotted lines go through all the points. And when we do the same thing for A1, we use a functional form that was developed by Gobati for the speed MD equation. That's where you might have seen this functional form before. And then we infer what each one of these coefficients is from expanding the power series and equating like coefficients. The only fudge factor that's in here is this delta 1. If it was 0, then we wouldn't be using any resummation or any correction at all. In order to make it go really perfectly through the points, I had to make it 0.5. If I made it 0, you would not see much of a difference. On the scale of this graph, you probably wouldn't be able to see the difference. And so we're getting almost a perfect prediction of the molecular simulation theory results from the virial coefficients. Here, I haven't used any empirical coefficients, and this is the prediction we're getting for A2. A3, I had to use a little bit of a fudge factor because, like I said, the third virial coefficient, I couldn't get that to work. And so I developed this correlation to estimate this G1 quantity. But again, the G0 quantity and the critical density, those parameters are set from the virial coefficients. There's only this little thing that I needed to add as we went up in temperature to get all of my different A3 contributions. And then this is what A3 looks like instead of just the ratio. Van Westen and Gross, in their paper, they say that there's this ansatz that this I times AI times AI minus divided by AI minus 1 should be independent of the index. Well, that would be true if we were talking about square well fluids because it's an exponential, and that's the right recursion relationship that comes out of the virial coefficients for the square well fluid. But really, our ansatz is that it's the second virial coefficient that determines the intercept, all right? And that we assumed that this G3 at the max value was a constant. That was the thing that was really an ansatz or an assumption. The part about the intercept being the second virial coefficients, that's not an ansatz. That's absolutely true. That's 100% rigorous. Okay, so so we wouldn't expect, you know, to see what they were proposing we would see, but because these coefficients along the intercept would be changing. But I had hoped that the magnitude at the maximum would have been sort of similar to the magnitude here, and then we could say that it's the same G1 quantity as we move up in order. And that's the part that I've got a doubt about based on the simulation results that they've performed so far. Nevertheless, just using the interpolations that I've shown you so far, we can compare what we get to the highest accuracy equation of state that's available at this moment. It's developed by Thole et al. So they use these multi-parameter equations of state to regress using derivative properties and everything that's known about the Lennard-Jones fluid with tail corrections, and develop a really rigorous NIST quality equation of state. And what you see is whenever we're outside the two-phase region, we get virtually quantitative agreement with their result. And what's interesting about that, we never used any results for the full simulation. So we never used any simulation results with using the full potential, but we're predicting the results of the full potential just by looking at the perturbation contributions of each one and the virial coefficients, which are very rigorous. So we're getting just about quantitative accuracy. The good news is, because the virial coefficients don't really have anything in them about metastability or anything like that, and we've used a very systematic theory, when we extrapolate our theory into the metastable region, it's very smooth, and we get very reasonable results. But if you look at, for artifacts inside the two-phase region with the Thole equation, Al Saifi has done this just recently, okay? It's a mess, okay? But when we do that with the equation of state we developed, there are no artifacts on the physical branch. Okay, so we've eliminated all of those weird things that are happening, which means that we can use this quantitative equation of state for applying density functional theory in the usual way, because we don't have to deal with any artifacts. Another thing that's in this paper, Al Saifi also looks at the equation of state by Johnson et al., Khalafa Nesbeta, Mecke, every equation state, pick your favorite one. He shows all the artifacts that are there for every other equation of state. And so one of the things we're going to do next is take this functional form that we have that's pretty good already, and we're going to refine it using the same kind of data that Thole et al. Used, and just go back and look at those little parameters like the delta 1, okay, and adjust those relative to the simulation results for the full potential, like Thole did. And I think what we're going to have then is an equation of state that's quantitative for every property, and at the same time eliminates all artifacts. We're going to see if we can also even eliminate whatever this weirdness is that's going on for the unphysical branch down here. So very near the end here, I've gone over time again, sorry. I've done the same thing, the same kind of analysis for Lennard-Jones chains, okay? And we see very similar trends, okay? So here we're predicting the virial coefficients for the reference fluid from looking at essentially an underlying hardcore chain, okay? So we've got to infer, well, what is that virial coefficient for that underlying hardcore chain? But once we know what that is, it's not a function of temperature, and we've got this universal equation of state that describes all the different temperatures and densities for the reference fluid. We can also develop correlations for the individual virial coefficient at each order in temperature, and then we can predict the A1 and the A2. As we go to longer chains, the accuracy of the virial series alone deteriorates a little bit, so our corrections need to be a little bit bigger. Works for the second order as well as the first order and the third order, very similar. Here we're seeing what appears to be a discrepancy for dodecane in what the intercept should be. So we have to ask the question, which one seems to have less uncertainty? The simulation results for the value of that intercept or the virial coefficient results? The uncertainties that Andrew Schultz gets from his program and his virial coefficients is much, much lower in the uncertainties of these simulation results. So my guess is this is the right value for the intercept. I told you I would talk about the second virial coefficient. It's so easy to calculate this on the fly doing any molecular simulation that you've got. So here's a snapshot for N-butane. This is a PDB file, okay? What we've got is 1,200 butane molecules, okay? And so here's one butane molecule. We've got the methyl group, two methylene groups, methyl group. Here are their positions in space, all right? And we do that for the second molecule. And all we have to do then is go through all of these molecules. With 1,200 of these, we have about 600,000 binary combinations, okay, that we're going to be summing over for all the IJ molecule combinations. We move both I and j to the origin, and then we move the I molecule one step in R away from the origin, okay? And then we calculate the potential energy between the molecules according to the trap potential, and then we add that to our average for the Meyer function, okay? We do that over all the ij molecules, over all the distances, and then we sum or integrate with respect to distance. That's how you get the second virial coefficient. That's how easy it is to calculate the second virial coefficient. And if you do the same thing for the reference potential, you'll get the B20. You do it for the reference potential times beta U, that'll be the first order, B21. Reference potential times beta U squared, second order contribution, okay? So these things are really, really easy to calculate. To be on the fly, technically you should be computing these things and putting them in bins as you're doing your MD simulation. But you can do it after the fact. It only takes you 15 minutes, but it might be kind of cute to add a little subroutine that computes these second virial coefficients on the fly anytime you do any molecular simulation, because they're so easy. And when we compare the second virial coefficients that we get from this on the fly algorithm, you know, just looking at one snapshot, it goes right through the points. Now, my uncertainties are larger than what Andrew gets, but the average values that we get are pretty close to the average values that he gets. And that's going to be a lot better than what we were getting when we tried to infer what the second virial coefficient is just by doing low density simulations with MD, okay? It turns out the uncertainties get really large, even with rigid bonds. It's even worse with flexible bonds. I didn't even show that picture. You can see more about this in this fluid phase equilibria paper, where we look at the isothermal isochoric integration as a means to calculating your vapor liquid equilibria, binodal curves, and vapor pressures and all of that, and using that as a tool for force field inference, okay? So if we put together these on-the-fly second virial coefficients with a couple more state points in this ITIC method, we're going to be able to refine the force field super efficiently by a combination of M-bar and second virial coefficients. So here's the summary then of the takeaway lessons. The point I'd like to make is to choose your physics wisely, okay? That will make it so much easier for your series to sum to infinity and get the high accuracy that you need from your perturbation series expansions, okay? So if you can get rid of this square shoulder, you're going to be a lot happier, okay? Another situation, if you use the Barker-Henderson method as your method for defining your reference fluid, that's what Jackson and that group does for their Saft gamma me theory, okay? You're going to have this problem again where you've got your second order contribution with these weird shoulders out here, and those shoulders out there are always going to give you headaches, okay? Whereas if you use the WCA definition, your perturbation expansions make perfect sense, and you can infer the results with just a few terms at low order in density. Interestingly, the virial series that you always heard does not converge for liquids. I say it does. But you've got to sum each order individually. The A naught term, the fact that that converges, I offer you the Carnahan-Starling equation as proof of that, okay? The A1 term, I've shown you. I hope I've convinced you. It sure looks like it's converging. The A2 term for square well spheres, that square shoulder is giving us a lot of headaches. But remember, I didn't use any empirical corrections. All I did was reorganize the summation, assuming an exponential functional form, and then use the virial coefficients that I had, and we got excellent agreement and an amazingly good equation of state, competitive with the best quantitative equation of state out there. So the renormalization that you use needs to reflect the physics of that order. So in the 0th order, it's the repulsive effect at close packing that's driving the renormalization. At 1st order, it pretty much converges, but you need a little help with the exponential functional form, okay? 2nd order, it's that exponential decay to 0. So at high density, the irony is, virial coefficients can't tell you what's happening at high density. But the irony is, nothing's happening there because the value of A2 is 0 there. So if you assume an exponential form, it will naturally decay to 0, and you only need to know the low density results, which the virial coefficients tell you perfectly. Okay, so by using the right physics where the decay is to 0, okay, then you only need to know the virial coefficients, and the series that you assume and the renormalization that you assume will take care of what's happening at high density. And we saw that A3 and A4 also go to 0 at high density. Hopefully I've convinced you that it's easy to calculate this B2 at every order, and it's informative, and it's probably something we should all be doing with every simulation that we do. And that once we do that, figuring out how to handle the binodal near the critical temperature is not really an issue. Okay, sorry, I talked too long again. Nothing I can do seems to help me.
Thank you, Professor Elliott, for this presentation. Very, very profound. We are running a little short on time. Some students had to go to class because they have it starts at 1 o'clock, but lots of professors are still watching us. So I think I will allow for one or two questions.
I have a question. Can I ask?
Yeah, go on, Professor Haja.
It's a very interesting talk, and the whole village is back again. Can you comment on, say, orientation interactions? If you have explicitly include orientation interactions, will the series still converge?
Yeah, so that's this theory of Smith and Nesbeta goes back to actually Smith's first paper was 1974, I think. And then in 1983, Smith and Nesbeta actually wrote a review article where they go into it. And they were applying it to spherocylinders. And they were able to show that for surprisingly large aspect ratios, just looking at this Meyer averaged potential function was sufficient. What they would do is calculate this ensemble average of the Meyer function, and then they would get a radial distribution function for the reference fluid, and then multiply it like the hard sphere fluid, and then multiply that. So it's called a total correlation function, I think, when you multiply the radial distribution function times the exponential of beta u for that potential function. So that curve is a continuous curve that goes all the way to 0. And so if you take that for the reference fluid and then multiply it by the potential function for the actual fluid, you get a very good approximation for the radial distribution function of the total fluid, of the potential of interest. And so that theory was examined a lot in the 80s and even early 90s. And I think Nesbeta is still using that approach for a lot of things, especially water right now. So it works pretty well, better than you might think it would, even for something like spherocylinders. And so one of the things that I didn't get a chance to talk about was the way that the virial coefficients, especially at higher order, are evolving. And it's like they're becoming softer. So for the chains, so for dodecane, at third or fourth order, what we're able to see is the second virial coefficient is not really repulsive. It's not diving to zero. It's not staying flat until you get to very high temperatures. It's diving to zero at a much lower temperature. So what that's saying is that these chains, if you think about trying to put together two hard spheres in the same place at the same time, you can't do that because they're so repulsive. But if you're putting together the center of mass of two chains, where the center of mass is for those chains, there might not be any atoms. So you could actually put them right where their center of center distance for the center of mass is right on top of each other. Because of the way that the chain is wiggling around, that center of mass doesn't actually have any atoms there. So as the chain gets longer, the strictness of repulsion of a chain like that is actually softer. And so you see that by computing this Meyer averaged potential function that you have to compute to get the virial coefficient anyway. So it's interesting to just look at that potential function that comes out of that and see what you can infer about the behaviors of these chains as they get longer.
So what you're telling is for smaller molecules, maybe spherical shell potential or something like that will be sufficient.
Yeah.
That's what you're saying. Like a center of force and center of mass just have one bond.
Right. And the chains are becoming kind of squishy from a center of mass perspective.
Okay. The other question is about thermal properties. You mentioned something about CV diverging slowly or becoming finite. Can you really calculate the specific heat using such an expansion?
It looks like we're not capturing that divergence. And so that's a case where you would probably need to add something like a renormalization group theory that's targeted just for that particular contribution. We did some work on that with square wall spheres, published in about 2006 in Molecular Physics with Sergei Kiselev. So if you search for my name and then Kiselev, you should be able to find that paper. Sergei's specialty was the renormalization group theory. And one of the things he always got very frustrated with was so many theories are second order, and second order is so far from the actual, renormalized critical point that he had to use really large corrections in order to get the behavior to be correct near the critical point. But by using this simple exponential Gaussian extrapolation, we're already very, very close to the critical point, and we might not need any renormalization with respect to the density. So the only thing we would need to add is the contribution that he had for the critical temperature. And he would be so happy right now because he could do that really super easily.
So finally, one more question. So what do you think of these Vidam lines and clustering above the critical temperature? Will it still continue? We can explain through perturbation theories?
I didn't quite understand.
Okay. Above the critical temperature,
Yeah.
There are things like Vidam line, say superclusters and clusters, structures, ordering.
Right.
That can be captured with higher virial coefficients, you think?
Yeah. So I think we can. Well, to really capture the heat capacity, okay, we're going to need something non-analytic for that. But yeah, I think we can get a quantitative equation of state that is as good as the Thole equation of state, and that's what you can use to look at your higher order derivatives to see if those Widom lines and who's this guy, Leslie?
Leslie, yeah, it's a white also is.
Yeah, yeah, White, I guess, has looked at a little
White
bit.
also has.
But Woodcock especially has come up with a lot of conjectures about the strange behaviors that are occurring there, and whether there are pseudo liquids out there, and the ways that those inflection points behave. Yeah, I think we'll get as quantitative as we can get. One of the things that Thole used as a way of getting great accuracy for derivative properties is there's a method due to Rolf Lustig, Lustig. Are you familiar with that method?
Oh, yes.
Okay, so he's able to simulate components of those derivatives that don't directly address the derivative for CV or the derivative for the compressibility, but there are pieces of those things. But each one of those pieces is very highly accurate. And then you can add them together after the simulation is done and infer what your heat capacity and your compressibility are and your speed of sound. And so Vrabeck is the only one who I know has implemented Lustig's methods into a molecular simulator, except for Lustig, okay? And Lustig went to work for Vrabeck to port everything into Vrabeck's MS2 code, okay? So they incorporated all of that capability to get all their derivative properties, and then they included all of that when they did their regression. So if there are strange behaviors out there going on, they're going to show up when you get highly accurate characterizations of those derivative properties. And we're doing better and better jobs of that.
Thank you very much. It's a very interesting talk. Finally, for us engineers, you really think PC Soft can compete with, say, fifth virial up to series of fifth virial series, or PC Soft is poorer than equation of state with fifth virial coefficients?
So if you add the Gaussian extrapolation onto PC-SAFT. PC-SAFT is a second order theory, right?
Second order.
It can't do more than a second order theory does. But if you put the Gaussian extrapolation on top of it, then yeah.
It's supposed to say third order or fourth virial coefficient maybe.
Okay, we're not going to get highly precise third order and fourth order virial coefficients, but qualitatively, I think we'll be able to get close to that.
Okay. Thank you very much. Very interesting talk. Motivating.
Thank you, Professor Roger. I think we can allow one more question, maybe from someone outside the UFRJ, outside Brazil. Okay, anyone from Brazil wants to ask the last question?
I think I have one, but he should talk about already. Maybe if someone wants to question something, just while we're waiting, he should, if I understood, your point is when you use Gaussian extrapolation, you are kind of renormalization, but in temperature. And when you use Wilson renormalization, the renormalization is in the space of densities. But in Wilson, when you go to mixtures, you have to do renormalization in each density component, like a density of component I. But here in Gaussian, you don't need this. It's in temperature, so it's the same for one component and for mixture. Is it?
Well, I guess it's similar to what Gabriel's working on, right? Is that if we have a mixing rule for how the Gaussian function, okay, how that behaves for mixtures, then we can calculate all the mixture properties.
Yeah, but in the sense of renormalization.
So it would.
You're talking about the procedure, but I'm not saying that. I'm saying about the idea of renormalization, because in Wilson you have to do, well, you can simplify that doing some scale, but I'm saying in the original idea is you have to do the renormalization for each density. Density of I. It's not, but in Gaussian extrapolation, you may not need that. It's only one renormalization, need for mixtures.
Yeah, so we're getting the entire density curve. We're getting all of that from the Gaussian function, right, at that order. So we're kind of automatically, yeah, let's see, are we recursive? Well, okay, yeah, I guess I'm saying something a little different in terms of recursion with respect to density. I'm inferring how that density behavior occurs by looking at the renormalization of the virial coefficients and figuring out what is it that makes that series converge. The virial series, the series with respect to density.
Mm-hmm.
Yeah, that is different.
We can think about this later on.
Yeah.
So I think it's time to wrap it up. Let us all thank Professor Elliott again for the presentation. Thank you.